All right. Hello, everyone. Welcome to today's Corundum status updates. Oops. Okay. If I can not make my window disappear, that would be a good start. Okay. Let's see. So for today, announcements, product ideas, and status updates. Just not a whole lot to talk about. Okay. So real quick for announcements, the next Switch development meeting will be in 1 week on September 18th. Unless there's a change of plans, and then the next Chrono developer meeting will be on September 25th. Again, same time, although I guess I do need to start checking. Some point there is going to be a time change, I think, coming up relatively soon. Definitely something to be aware of. All right. So going over the project ideas real quick. This is something that I've brought up the last couple of meetings, just if anybody's interested in getting involved in Corundum and working on something, and you want, say, a relatively self-contained project idea to chip away at, here's a few ideas. I'll just go over these really quick at a high level. First idea here is oversampled 1000 base X on a 10G base ARC receiver. Under certain conditions, reconfiguring the serializers for operation at rates other than 10G or maybe 25G is not particularly feasible. So, okay, is it possible to take a transceiver that's configured for 10G and run it at 1G? Definitely something that's worth some experiments, and if it works, that could be a nice feature to implement into Corundum. And maybe there's ways of even running it slower, or potentially some other line rates other than 10G. I think the 2.5G and 5G could also be worth looking at, perhaps. Next up, open source 40G Mac plus PCS. I've seen some code floating around for some pieces of 40G Mac plus PCS. It's possible that if we take all those pieces and put it together, we'd have a usable Mac. It's also possible there'd be something missing. So that's definitely something worth taking a look at, because I've had a couple people ask about, support for 40G and Corundum. Either taking those pieces, putting them together, and having a 40G Mac, or using them as a reference to build something from scratch. That could be a pretty interesting, somewhat straightforward project. 40G is not as straightforward as 10G or 25G, but at least it's a lot simpler than 100G, particularly because it doesn't require RS-spec. Let's see. Next up is basically switchable wrappers for various line rates, where you can combine the 100G CMAX, 10 gig, 25 gig max, potentially 40 gig max, potentially, gigabit support, all into one module where you can reconfigure it to run at whatever rate you want at runtime. This is similar to what a lot of devices do. Like a Mellanox NIC, plug the cable in, it'll run at whatever rate you want pretty much. It would be nice to have similar capabilities in Corundum. Another point on here is the RISC-V management core to manage board level stuff. The idea with this is to make the driver completely board independent by taking all of the board dependent code and putting that in a soft core running on the FPGA. So something I've been meaning to work on for a while, but haven't had time to sink my teeth into it properly. I guess I could expand on this a little bit. I'm also considering bringing in a data path management core as well, and most likely keeping those as two separate cores. But that's probably a point of further discussion at some point. Another thing that would be nice to have is just kind of an open source JTAG adapter with the Alveo connectors. So not only for the U50, but also for the SN1022 that has a little high density edge connector. It wouldn't be hard to spin a little board with a couple connectors on there, plus one of the FTDI USB JTAG chips, and then we can have a little board that's compatible with Vado. Wouldn't only cost a few bucks, and then could be used for all the Alveo boards, as well as put a regular JTAG connector on there. You can use it for other stuff as well. So that could be kind of a fun little project. Also with Corundum right now, the transmit scheduler is very simple, just very simple round robin, not particularly configurable. Gets the job done, but there's a lot more you could do with a with a more flexible scheduler. So if somebody has wants to work on a scheduler, that could be a fun project. Build a new scheduler that does, say, weighted fair queuing, can implement rate limiting or something. We can swap out the standard Corundum scheduler for something better. Another project idea, SRIOV support, adding support for multiple PCIe virtual functions, such that you can have multiple virtual machines or whatever connected to the device and communicating with their own self-contained network interfaces. But this does touch a lot of internal components to work properly. Another component that somebody mentioned would be interesting to work on is multi-head support. So basically multiple PCIe and or AXI interfaces, such that you can have multiple hosts interfacing with the card at the same time. Similar to SRIOV, but some differences. And then another point here is improved application section SoC support. Like, do we need to add additional streaming interfaces or AXI interfaces or something for SoC type devices? They'll have, in some cases, like cache coherent ports. Exposing some of those to the application section could be quite useful. All right, so that wraps up the project ideas. Also, if anybody has any additional ideas, feel free to pass them along and I'll add them to the list. Or if anybody wants to work on one of these, let me know. And if it's implemented, we'll take it off the list. Anyway, moving on. Status updates. So, a number of things to talk about today. First is Mac control and PFC. I think I have that mostly implemented at this point, although there's probably a few straggling odds and ends that need to be tweaked. More details on that in a couple minutes here. I'm also just going to detail some of the updates that I've made to Corundum, including the Mac control and PFC stuff, but a couple of other things as well. And then I'm going to talk about some potential timestamp handling improvements that I've been thinking about, as well as some architectural changes in Corundum that I have planned. More details on that in a couple slides here. All right, so for the Mac control and PFC pause frames, the idea behind this is to provide link layer control or link level control for Ethernet. So the receiver can send a message to the sender saying, hey, hold on, stop sending for a bit. The Mac control layer is what's responsible for sending and receiving these messages, because they're not supposed to be sent to the network stack. They're just supposed to be exchanged between the Macs. And this has to be done very close to the Mac because they have to be able to skip over whatever might be in the transmit or receive FIFO for the lowest possible latency. Well, I guess for a reasonably low latency. If you want to get the lowest possible latency, well, now you're talking about other optimizations you might make, in the HFT space. Anyway, so in Corundum, I have the Mac control layer implemented to send and receive pause frames, and that I've rolled that into the 25 gig Mac core that I use, and then I've also gone ahead and wired up the pause control signals from the CMAX and the other hard Macs, and all that's been integrated to support sending and receiving at least standard pause frames at the moment. PFC frames are going to require more work in terms of actually supporting traffic classes in Corundum, because if you don't have traffic classes that you can pause, then PFC doesn't really help you very much. So at some point we'll have that implemented. I don't have a timeline for that at the moment, but the testing that I've done does seem to show that pause frames are doing what they're supposed to do. The test setup that I used, I had a 1 NIC configured for transmit, basically in a Gen 3x16 slot, and then a receiver NIC running in a different slot, this one being a Gen 3x4 slot. So the idea is that it's not going to be able to run at line rate, so it's going to have to send a lot of pause frames. So we're going to send traffic from the TX to RX, and then RX is going to send pause frames back to the TX side and control the rate. So with Corundum operating as a transmitter, handling pause frames from Mellanox NIC at the other end, that seems to be lossless. iPerf doesn't report any retransmits under that particular mode of operation. If you switch the NICs and have Corundum generating PFC pause frames back to the Mellanox NIC, Um, it doesn't quite work as I was expecting because there are a few retransmits. I need to pin down on where those are coming from though, because one other difference is that Corundum is not doing any receive side offloading aside from checksumming. It just hands all the frames off to the operating system. So it's possible there's something going on with like the frame rate or something causing the operating system to drop a few packets, causing iPerf to retransmit. I'm not 100% sure about that. I'm going to see if I can pin down what's going on there. Or at least verify that, or at least see if I can figure out these packets are being dropped in Corundum or somewhere else. But one thing that I did notice is that there's a huge difference on the data rate between having pause frames enabled or not. I think in the testing that I was doing, I was seeing something like 14 gigabits per second with pause frames disabled. And then if I enabled them, it was running fast, running more like 19 gigabits a second. And significantly fewer packet drops, not zero, but well, okay, significantly fewer retransmits. I should be clear here. Significantly fewer retransmits, but not zero. So I might need to do some playing around with things as well, because when generating pause frames, it's also going to be dependent on like the buffer size and the watermark setting. You know, at what point in terms of fill level are we generating this pause request? So a couple of other things to play around with. And the other thing is I think I need to go through and probably increase some of the buffer sizes as well, because previously all the RX queues I think were set at 32K at 25G, and that seems to be too small. It probably needs to be closer to 64, 128. So I'm going to do some playing around with that and probably update the buffer sizes in a bunch of designs to help with that. Because it's a larger buffer size and you have, you know, more time to react, basically. I did make the watermark setting adjustable with a register, so I can also try playing around with that a bit. I have not done that yet, though. Anyway, that's summary of the Mac control layer stuff. That's pretty much implemented at this point, and that's been pushed up into my development repository. All right, so moving on to just general Corundum updates. So, like I said, the PFC, the pause frame and Mac control layer support have been added to Corundum. There's a couple different pieces to that. One of these is an internal Mac control layer, which currently is not being used outside of a couple of the test benches. But the internal Mac control layer is available when you're running on a device that, you know, doesn't have PFC support in a hard Mac or something. So, you know, you could potentially use this with the CMAC cores or something when, you know, if the hardcore doesn't support sending and receiving this Mac control traffic. But it seems like a lot of existing Macs support that. You just need to connect the, you know, pause request lines to the core. I also implemented new port control registers into the port modules for controlling the pause frame and PFC frame support. So with these registers, you can adjust the watermark setting, you can enable or disable flow control. I also added RX enable bits and RX pause bits, so you can, or RX and TX enable and pause bits, so you can basically stop the flow of traffic through the data path. So this is, I think, going to be quite useful when you don't have all the ports configured, but there's data coming in one of the ports. Well, with the RX enabled bits, you can turn that off, so that data is not causing trouble in the data path or getting handed off to the software if we're not supposed to be receiving any data from that port. So that's been implemented and integrated into Corundum. I've also gone through and updated all of the individual target designs to add support for pause frames and PFC frames. There's a couple of parts to this. One of them is adding a couple of parameters to configure things, and the other thing is adding all of the necessary connections to all the Mac modules. So for the CMAX and for the E-tiles, you know, this means stringing a bunch of additional signals through the top level and hooking it up to the hard logic. So that's done at this point, and things seem to be working as expected both with the both in the TX direction and in the RX direction. I guess I need to check with the e-tiles in generating pause frames. Haven't done that yet, but in the RX direction, handling pause frames, it seems to work correctly. And for Xilinx devices with I've tested both with the CMAC and with the 25 gig softmac, and that all seems to work. I also, it was reported there were a couple issues with the PCIe class code, and previously I'd noticed a problem with subsystem vendor IDs on ultra-scale devices, and I think I've fixed both of those issues. The problem with the ultra-scale devices is that subsystem vendor ID is set by a port, and I completely forgot that port was there because documentation doesn't talk about it. But when I looked at the code, I'm like, oh, I see. The vendor ID is being set right here. So I just set it based on the board ID parameter instead of having a static value. So that appears to be working correctly, and that explains why it was showing the wrong value on all the ultra-scale devices. For the ultra-scale plus cores, there's like an option. If you check a particular box, then it exposes, I think, all of the IDs as ports, so you can just tie them off statically. But for ultra-scale devices, one, there isn't that checkbox, and two, it always exposes specifically the subsystem vendor ID as a port. I don't know why. And if it always exposes a port, then having the subsystem vendor ID box in the UI is kind of pointless because it doesn't do anything. So it seems like they could improve that a little bit. Anyway, I also suspect that the problem that we were seeing with the class code is that it's possible under newer versions of Avado, there's a little class code configurator thing that gives you some drop-down boxes that I think the default value for whether that's enabled or not got flipped. And for whatever reason, I didn't have that setting in all of the TCL scripts. So when you run the script to create the PCIe EIP core, it uses the configurator instead of putting in the raw value, and then you end up with the wrong class code. So I suspect that's what's going on. I haven't had confirmation that adding that line fixes the problem yet, but I think that's going to fix what we're seeing there. All right. So that rounds it out for the updates to Corundum. Now let me talk about a couple of the other changes that I've been mulling over. So the first one here is some potential improvements to handling PTP timestamps. And I talked about this a little bit last time around, but I've done a bit more ruminating on this and so expanded on this a little bit. So the key point here is that PTP timestamps are quite large. So there's a 96-bit time of day timestamp that's 48-bit seconds, and then 32.16 fixed point nanoseconds. And then there's also a relative timestamp that's 64 bits, and it's just 48.16 fixed point nanoseconds. With both of these, the MSBs are basically constant when you're operating at high data rates, because how long are you going to be hanging onto a packet for anyway, inside of an FPGA or integrated circuit or whatever? You don't have all that much SRAM to store packets, so if you're capturing timestamps, you don't necessarily have to capture all of the MSBs if there's a way to, say, reconstruct them, right? If you have a packet for less than a second, well, then you don't have to store those 48 bits worth of seconds. You can read that out of the PTP clock whenever you need it. So the question is, can we save some logic resources by truncating and reconstructing the high order bits of the timestamp? And the other thing that I was thinking about as well is, well, could both timestamp formats be supported efficiently? I think for a lot of applications, you want to use the 96-bit timestamps because that's your just straight up time of day timestamp. But there are definitely some use cases for the 64-bit timestamps, and there are some advantages, from a math perspective. That one rolls over as expected. So that potentially makes things a little bit simpler. So the question is there a way to support both timestamp formats, using the same logic? So if you need the 64-bit timestamps, they are there, and it could also simplify some things, even when you're using the 96-bit timestamps and you don't need the 64-bit ones. So for a scheme to work, we need to be able to handle when the MSBs actually update, when it rolls over. We need to be able to cross clock domains potentially, and we need to be able to handle long wires that might be going, way long distance across a device. So the first point here is supporting both 64 and 96-bit formats. So the 96-bit format is difficult to truncate beyond, dropping the seconds portion of it because of how the rollover works. With the 32-bit nanosecond field, that rolls over at 1 billion. It's not a power of 2, so you have to do some more complex logic to make that determination, right? You got to check to see, is it greater than 1 billion? If so, then you have to subtract 1 billion and use, that value instead of just a nice power of 2 rollover. So the idea I had is, okay, well, what if we define the 96-bit timestamp as an offset of, a truncated version of the 64-bit timestamp? Say we'll take 48.16 fixed point nanoseconds, and then we'll just add an offset to that to get the 96-bit timestamp, and then you can add the MSBs to that to get the 64-bit timestamp. Obviously, the offset is going to change every time things roll over, but there's potentially some advantages to doing something like that. First is that you get kind of natural binary rollover, so the offsets are relatively easy to apply. And also, the timestamp logic, it only has to handle one timestamp format. You don't have to have two sets of timestamp logic, one of them for 96 or one for 64, or some way to switch which format you're using. You can just do everything with this truncated 64-bit, and then from that you can regenerate. Do you want 96-bit or do you want the full 64-bit? Another advantage is that 64-bit timestamp format can be completely monotonic, right? You're not going to be stepping that. You might get slewed. You might be changing the rate that this thing is incrementing at, but you're not going to be stepping it to set some random time. So that could simplify things in terms of some of the PTP, CDC logic or whatever. Next point here is that the offset changes with the rollover and with time changes. So if you're defining your 96-bit as an offset of the 64-bit timestamp, well, every time, every second, you're going to have to update that offset. But, that's not that big of a deal, I don't think. You can kind of use the same technique for keeping track of that as you do for the, MSB reconstruction. And then what you can do is you can distribute the offset along with full reference timestamps to all of the components in the design that need to be generating these full timestamp formats. Next question is, okay, how do we transfer this stuff around on the device? So my original idea is just for, reconstructing the MSBs. We don't need to transfer the whole PTP time. We just need to transfer a subset of the timestamps. So the idea here is you split the timestamp into two portions with some overlap. So for example, you take your 96-bit timestamp, you whack off the seconds portion, so you can transfer the nanoseconds portion, normally, and then the seconds portion that would be transferred via some other method. And you would have a couple of additional bits of overlap to determine when there is a rollover such that you can use the correct MSBs. And the number of overlap bits determines kind of a window for reconstruction of how many rollovers of the truncated portion you can handle before you run out of, or you start running into issues with aliasing. In this case, the timestamp capture logic is only going to handle the fine portion, so that's going to reduce resource consumption. It's going to make all the FIFOs smaller because you need less sideband data and whatnot. And then the coarse portion will be transferred over a slow serial link, similar to SPI. So if we're just interested in transferring the MSBs, kind of my idea here is to run this really slow, so we don't need to worry about PTP, CDC logic, or pipelining or anything like that. We can just basically timing ignore it and everything should work. The hardware clock is then going to shift out two coarse timestamps, the current one and then a subsequent one after it's incremented. And then the reconstruction logic would store several of these timestamps in LUTRAM indexed via these overlap bits. And then the reconstruction is just a table lookup, right? You get the truncated timestamp. You look at the MSBs of that. That determines which entry in the table to use, and that gives you the MSBs that you can just combine, and you're done. But if we're going back to the idea of, both 64-bit and 96-bit timestamp support, maybe there's a slightly different approach that can be taken. So if we're just talking about MSBs, we can run everything really slow. We don't really care about delay and whatnot. But another possibility is, well, why don't we use a faster serial link and actually use this to synchronize the PTP time itself, as opposed to just transferring some of the MSBs for reconstruction. And this could simplify some of the other connections as well, because with the previous setup, you still need to get, say, the PTP time to the Ethernet MACs, which are going to be completely on the other side of the device, potentially. So is there a nice way of doing that? I kind of liken this to what you might see at schools or train stations a number of years ago, where they have clocks that are synchronized to a central office, and they use a very simple mechanism for making sure the clocks are showing the same time. So the idea is kind of to do something similar here, where we have the PTP hardware clock that's keeping track of the time, and then it has this very simple serial link which connects to multiple clock modules at various locations on the device, which can then reconstruct the PTP time, and then tick in lockstep with the main PTP hardware clock. So in order for this to work, we need to distribute a PTP reference clock across the entire device. In this case, I'm talking about just an external reference frequency that drives the PTP hardware clock, and will also drive these secondary devices as well. Then the second part of this is to run the hardware clock ahead by a number of clock cycles. So maybe 256 clock cycles, something like that. If you pick a nice power of 2, then it makes it easier to compute the new PTP clock time. And the reason you run it ahead is so you can send you can do something similar to those talking clocks, right? If you've ever used one of those before, right, you dial a number and then you hear a voice at the other end saying at the tone, the time will be 9:36 a.m. and 0 seconds. The idea is to do something very similar with this serial protocol, where we transfer all of the timing information, and then we have a reference edge that's used to latch it into the clock. So what's going to need to go in here? Still trying to get that figured out, but we can send reference timestamps for both 64 and 96-bit formats. We could send the offsets, right? We can send the LSB portion of the timestamp that's changing quickly. We can send the step value as well, that's used by the hardware clock, the part that you're actually adjusting to change the rate that the clock is running at. All that stuff can be sent down this serial link. And then the endpoint clocks, they can accept this data and then latch it based on the reference edge. Another component to this is, well, if you have like a big pipeline delay because you got to go all the way across the chip, is there a way to compensate for that? And yeah, I think there's a pretty straightforward way of doing that, actually. If we send the reference edge early, say 32 cycles before you're actually supposed to latch it, then it's simple to have a little counter that can delay when the actual latching takes place. And then you can delay by 32 minus the minus whatever pipeline delay that you have, such that everything latches the time at the same time and then runs in lockstep. So this is, I think, going to be a pretty useful method for, at least in the switch design, when you have 32 or 64 ports, and every single one needs to have its own local time reference on both the TX side and the RX side for timestamping. This, I think, could be a pretty efficient way of making that work. And then these little local clocks, they can generate whatever timestamp format is required. Do you need 96-bit? Do you need 64-bit? Do you need, truncated timestamp that then can be reconstructed later? And you can pare the logic down to exactly what you need. Additionally, at the endpoints, you'll have access to the full 32-bit fractional nanosecond value instead of what's usually in the normal PTP timestamps, which would just be 16 bits. So this potentially opens the door to improving accuracy of various things. If you have the full value available, one, you can capture higher resolution timestamps, potentially. I don't know if it makes much difference. 16-bit fractional nanoseconds is already pretty fine. But it could also potentially make a difference with like the PTP clock domain crossing logic to get a better read on the delay between different clock domains. Not 100% sure about the utility of that yet, but that is a characteristic of this particular method. So I'll definitely be doing some experiments with that relatively soon here. All right. So now on to some of the architectural changes that I'm thinking about. First thing is migrating to using a single hardware interface instead of multiple. So currently, Corundum supports basically a parameterizable number of interface modules. Each one of these is what manages all of the queues and whatnot. And with each interface potentially connecting to multiple ports. But with some of the other changes that I'm planning on, the question is, is this really necessary? So the new queue management logic that I've been working on, it basically trades area for performance. It takes up more logic resources, but it provides, some descriptor caching ability. Hopefully it's going to be improving packet rate and whatnot, but it takes up more area. So if we just have one interface on a device, then that's going to be more reasonable than if we got to go, all right, well, there's 2 or 4 interfaces. So if we take up too much additional logic resources, then that's going to be a problem. But yeah, that's definitely an important consideration. Another aspect of this is now that we have dynamic queue allocation support in the driver and RX indirection tables, so that software can more easily manage all of the queuing resources and whatnot. Well, it's now possible to smoothly expose each port separately as an OS level interface and deal with all that through software, as opposed to having these interfaces at the hardware level. Obviously, you're going to be sharing more logic between the ports, which you potentially run into differences in performance. But at the same time, by sharing the logic, you are reducing the footprint on the device. And then another aspect of this is if we're going to add, an embedded switch of some sort, then it's likely going to make even more sense to manage all this stuff in software. So at this point, we don't have all the details yet on exactly how that's going to look with the packet switch project and how that's going to be integrated to the rest of Corundum, but that is definitely something to think about. So I think the folks at MLE have been running in this configuration where they have one interface and then they're registering multiple basically NICs at the operating system level. So I think the idea is just to basically do the same thing upstream instead and support that natively, and that could simplify a few things. So yeah, that's the first change that I'm thinking about making here. The second one is starting to think about how the switch integration is going to work. So we've discussed this a little bit. Carlos has been working on basically building a packet switch on FPGA with the intent of, once that's working, we're going to integrate that back into the Corundum project. And that opens up the possibility of sharing code between the NIC and the switch. And there's a couple of components to that are worth thinking about a little bit from the standpoint of how this would work with Corundum. The first one is the port modules. So for the switch, it's going to be quite useful to be able to, say, take a 100 gig port and run that as 4 25 gig ports, or, well, 4 separate ports of potentially lower speeds. Could be 25, could be 10, could be combination, could be even slower. But the question is, okay, if you're going to do that, how are you going to connect that up to the switch and also to Corundum? So with the switch, I think the idea is going to be to do all of the aggregation across these multiple ports internal to this port module, and then we'll just have effectively a single 100 gig port that connects to the switch. But then with Corundum, the question is, how does it integrate along with the application section interfaces? Because the application section, it basically has the ability um, to look at packet data at 3 different points in the data path, right? It can look kind of at the interface level, but then it can also look kind of at the MAC level, both synchronously in terms of the core clock domain or asynchronously, synchronous with the MACs. So if we're going to handle splitting a port between a single 100 gig port and 425 gig ports, the question is, how are we going to connect that to the application section? Are we just going to show the aggregated interface, or are we somehow going to provide access to the, kind of these internal 25 gig max when those are being used? At this point, I'm not sure what's going to make the most sense. I don't know if that asynchronous interface is just not going to be usable um, when we're doing this port splitting, or if maybe we'll have to add an additional set of asynchronous interfaces. So we have the 100 gig ones, and then we have the port split 25 gig ones. I mean, I think it would be somewhat reasonable to only have the asynchronous interfaces support the aggregated traffic and basically make them the same as the synchronous interfaces. Because that, let's see. Yeah, because if you did want the super low latency stuff, then you could just go with 25 gig only without the port splitting, and then you would have direct connections. And that would probably be a cleaner design, but not sure. There's a couple different directions that we could take that in, perhaps. Not sure if anybody has any opinions on that. But another component to this is having the embedded switch for internal routing, SRIOV, etc. Yeah, I think this is probably going to be the only way to really implement SRIOV, is to have some kind of embedded switch that can manage communication between the VFs as well as, taking the incoming traffic and sending it to the correct VF, and handling all the multiplexing stuff. That's kind of important. But if we're going to have this embedded switch, well, we can also add additional switch ports to the application section for application-specific logic. So that could be a pretty useful capability. In this case, you're not going to be trying to merge your traffic in with the outgoing traffic or something from the application section, but you'll have just your own dedicated switch ports that you can interface with. That's something to think about as well. I think that would be a pretty straightforward thing to do. Although it does definitely bring up the question of, how is this going to be managed? Another aspect is clocking. So with the switch, we're probably going to be using some additional clocks. So the question is, how is that going to affect the application section interfaces? I don't know if I've talked too much about the switch design yet, but basically the idea is that there's going to be a relatively high-speed core clock that's driving the effectively crossbar portion of the switch, where we're using these memory-based switches with a speed-up factor. So that clock could be even 500, 600 megahertz, depending. It's going to take a lot of timing optimization, I think, to get to that point, but it could be a pretty high frequency. But then there's also going to be kind of an intermediate frequency that's going to be used to manage aggregating the traffic from multiple input ports, as well as that's where the route compute logic is going to be implemented for actually processing the packets that are coming in and figuring out what port they need to be sent through. And that clock is probably going to be in the 300 to 350 megahertz range, something like that, which is faster than the 250 megahertz core clock. So this does raise a question in terms of the synchronous interfaces into the application section, because currently those are running at the same frequency as the PCIe core clock. So everything's running at the same frequency. But if we're going to run that at kind of this intermediate switch clock, well, do we need multiple additional clock domain crossings for that to work? Or does it make sense to run the synchronous interfaces at a, to decouple the clock there and run that at a higher clock frequency? Or another option potentially is to decouple the PCIe clock from the core clock, so we can actually run the core at this intermediate clock frequency, which could be faster or slower than the PCIe interface. So if we did something like that, then that actually wouldn't change the application section. It just wouldn't be synchronous to the PCIe clock. It would be synchronous to this internal switch clock. Not sure what makes the most sense here, but I'm trying to figure out what all the options are and sort out what's going to make the most sense. I think I have one more thing here. All right, yeah. Another thing that came up recently on the Zulip is providing more connections into the application section from the top level files on the design. So if you're doing something funky on a particular board and you got to add a lot of additional board specific logic, I don't know, we're talking about additional interfaces or additional processing or whatever, it might make sense to pass a lot of additional stuff all the way down into the application section. But that has to go through several hierarchy levels in the Verilog, and making that modification is tedious. Unfortunately, I'm not really sure of any really clean ways of doing this sort of thing with Verilog. I guess if you were using System Verilog or something, you could have I guess some sort of a record sort of format that you could swap out that record and then be passed through, and then you can add your signals to that. Unfortunately, we can't do that in the current setup. So we're trying to think of possible alternatives for that. And one idea that I had is, well, maybe this could be done with macros. I'd be able to include a couple different files, one of them with port definitions that gets included in the module port list, another one with port connections that gets included in the instance port list. Seems like that would probably work. I think it requires a little bit of testing just to make sure it's going to work and make sure it's going to be relatively clean. And then there's also a question, I guess, about parameters. You could import 4 files with 2 more handling the parameters. I'm not sure if it makes sense to do that or not, but yeah, I think Ulrich said he was going to take a look at this. I guess he's not on the call right now. I don't know if Joachim knows anything about that, but that's another thing that I've been trying to figure out as well, if there's a nice solution for doing this. So anyway, that's about all I got in terms of status updates and some of the, forward-looking changes. So if anyone has any questions or comments, anything they want to bring up, go ahead and fire away. Like nobody stopped me earlier going through any of the architectural stuff, so I guess that seems reasonable to everybody. Although on the flip side, we only have like 3 other people on here right now, so not a big turnout today. I guess maybe it's the holiday season a little bit, not sure. No questions or comments? Okay. Let's see, is there anything else to bring up here? I don't think there's anything else on my end at the moment to discuss. So if nobody has any questions or comments about any of that, then I guess we can adjourn for today. I don't know, Joachim, do you know if you guys have taken a look at the macros at all, or if maybe Ulrich was working on that?
Yeah, I guess I can say we thought about it, but I think we did not yet come to a conclusion.
Okay.
So, I mean, from my perspective, a macro solution, yeah, can be kind of obfuscating things. So it's not obviously right away visible what's going on in this section. On the other hand, yeah, it's one solution. We just
Right.
talked about it briefly, Ulrich and I, so
Right.
no
Yeah, I was
new
thinking that's kind of
thoughts.
the most straightforward thing that I could think of for just adding, arbitrary pass-through stuff. Because we could certainly go and add, AXI and AXI stream and whatever, but at some point it just gets ridiculous adding a bunch of
Yeah.
additional interfaces that the application section may or may not use. So yeah, it'd be nice if there was a better way of handling that. And I guess you could rewrite the whole thing in System Verilog or VHDL
Yeah.
or something, which would have potentially some other methods for handling stuff.
One possibility we kind of thought about, but only very briefly, would be to include one big with configurable vector, so that the user would have to select in slice in and out of
I
at
thought I already
the ends.
had something like that. I did have like a GPIO in and out thing, which would, I
Yeah,
guess you could
right.
basically use as something like that.
But we were not convinced of that
Yeah, it's one of those
completely,
things
because
like
it needs an adapter kind of thing at both
right,
ends.
yeah. It's one of those things that it would work, but it would be a pain to debug.
Yeah.
And it wouldn't be very clean, yeah. And also there are, I know, limits on the width of wires in HDLs as well. I think the limits are pretty high, but there is a limit there. So depending on what you're trying to send through there, you could run into that limit. I want to say it's like 2 to the 16, which is probably like way more than you guys might need, but
Yeah.
it is something to be aware of. Anyway, something to think about. And yeah, if you guys do end up prototyping something and it's relatively clean, then we can potentially pull that into the Corundum design directly, because that could be a pretty useful capability. I guess another possible solution is to kind of invert the problem and present basically all the application section interfaces at the top level, such that you're no longer running in the application section. Corundum is now just a block in a higher level design. Because if you're doing a bunch of really board specific modifications, it probably doesn't make sense to try to use the application section in Corundum. It's kind of the whole point of that, is that it doesn't matter what target you're running on. It's these are all standard interfaces that everything's going to provide. But as soon as you move away from that and you're trying to do something really board specific, then maybe it doesn't make sense to use the application section. Not sure. Anyway, I'm not sure if there's anything else that folks want to discuss.
Just to mention that, yeah, I really like how you explain all the changes that you want to do for the PTP stuff. I mean, I find it very interesting. And
Right,
also
yeah,
very
yeah.
important also for Corundum and also for the Switch. I mean, I think it can work very, very fine.
Right, yeah. We'll have to see how all the Switch stuff is going to end up fitting into the rest of Corundum. But yeah, I definitely think it makes sense to try to minimize the amount of stuff we have to rewrite. So if we can try to write something from the get-go that'll work for both, like new port modules or whatever, then I think that's definitely going to be the way to go. Because yeah, I think that that's just going to end up being a lot more flexible going forward. So
Yeah, I think that's for sure.
all right. Well, it's also nice to know that you did manage to get back to Spain safely. So long flight, but you're there, so that's good.
Yeah, almost get the first flight. But yeah, finally. So
All right. Well, hopefully you guys get your nice new high-tech global FPGA boards soon, because you'll probably have a lot of fun with those. Oh,
yeah, I have
was it?
heard they have already, I think, sent it to Spain. So
Oh, okay. So
hopefully
hopefully you'll get those
in 1 or 2
pretty soon.
weeks. Yeah.
Sweet.
So
That'll be good.
apparently sooner than we were expecting. So
Right. Oh yeah, another random thing that I should mention that me and Carlos discovered is that you can actually get the 1 millimeter pitch ribbon cable in the fancy
Oh.
rainbow colors. So you can have real snazzy JTAG cables if you get that instead of the gray stuff. So,
I like it. I like it.
yeah, definitely more interesting than the drab gray, and then the cost is, at least from DigiKey, is basically the same. So it's like, okay, well, might as well have some fun if you're gonna make some JTAG cables.
Yeah, I came to the lab last Monday. I saw my old programmer with the gray cable, and I brought my new rainbow one. It's like I can
Lock it
throw
out. Yeah,
another
nice.
one.
A little bit more fun.
Yeah.
All right. Well, I guess if we're out of stuff to discuss for today, then we can adjourn. And I guess, Carlos, you'll be heading up the Switch development meeting in a week, and then in 2 weeks we'll have the next Corundum development meeting.
Yeah.
Sound
Hopefully we
reasonable?
have some people in the Switch development meeting. Because I think we have maybe also good stuff to discuss.
Yeah, that'll be good. And well, hopefully you have your board by then too. We'll see.
Yeah. Let's see. Yeah, it could be very good. And yeah, maybe I can also this week try to order the tester, because I'm now trying to negotiate with them. So
Right. Okay. Well, hopefully that goes well.
and soon we can have everything also here prepared.
All right. Sounds good. All right. Well, I guess we'll go ahead and adjourn for today and see you guys either next week or in 2 weeks, depending. If you're interested in the Switch, we'll see you next week. If you don't care about the Switch, we'll see you in 2 weeks. That's how it's going to work. All right.
Okay. See you.
Talk to
Thank
you
you.
guys later.
Sounds good. Thanks. Bye.
See you.